Uh, my name is Damini Gupta and I work in the AI ML space. I am relatively a new entrant in this space, but one thing that really fascinates me about AI and ML is the sheer ability of the models to come out with good solutions, with a good acceptable solutions. And one thing which had been bothering me since the time I have moved into this AI ML space has been the unexplainability of the models and inability to add the domain knowledge to the models that have been built using AI and ML, and my frustration at mindlessly running the models again and again in that elusive search of a better model, better specificities, better sensitivities, better accuracies and all, without really knowing why am I doing it. It isn't a brute force approach, machine better than me. So as a data scientist, I should be able to add some value somewhere rather than mindlessly just running the model one after another and one after another. That is what led me into this topic of explainable AI, which is unraveling the enigma of AI predictions, and that's what I would like to talk about. Why is it important to begin with, what is explainable AI? Why is it important and how do we go about doing it? So in brief, what is explain? The agenda, as I've said, is already about the challenges, the solutions, the problems and the meaning. Okay, so what is explainable AI? If I ask you as data scientists, how many of you have had that same frustration that I had? Mindlessly looking at the models, mindlessly just running one after another in trying to prove it. Show of hands, how many of you have had that? And you're just like, yeah, absolutely, you feel like, why am I there at all, right? Let the machine do its job. Let it put it in a loop and run. Okay, and that's what it is. So now, explainable AI, it is an attempt to make the model output explainable in a way a human being can understand. In a way, I would look and take a decision. I want my models to do that and to be able to communicate and tell me why they took a decision. Remember the frustration we have had when our moms told us, I told you so. The model seems to be doing the same to me right now. I told you so. Right? And that's the frustration we want to get out of. Okay, I show you these pictures. What do you see? What do you see here as in these pictures? A bird, right? If I ask you to drill down a little more, some kind of a water bird, right? Why would you say it's a bird? Why did you call it a bird? Correct? You looked at it because it has a body, it has eyes, it has beak, it has, most importantly, it has wings. Right? A beak and a wing being a defining features. What did you bring in to call it a bird? You brought in your domain knowledge. So there are two aspects to it, and we need to understand a difference between an explanation and description. Had somebody asked you to describe, you would have said it's an object. It has a cylinder-shaped something to see which is probably an eye, something which is looks like some shape something, a lot of blue background in the, and that's how you would have described the image. What made you call it a duck or a bird is the inherent knowledge that you had about what a bird looks like, what a duck looks like, right? And that is where the challenge AI runs into. It runs into, it can describe an image, it can label an image. Can it make the two come together? And that is what explanation is all about. Explanation is all about being able to marry the label with the defining feature of an object. And that is where the explanations and the explainable AI come in. Okay, some of you gave me an answer, it's a duck, when I prompted you, right? When you say duck, you're differentiating it with respect to a parrot or a sparrow. And more so because of the presence of water and the bird is in the water, right? Also, some of you would have in the left two images looked at the shape shape of a beak and said, yes, there's something about what I see in a duck, right? Okay, now these are the biological names given to these set of birds. Again, we are looking at the defining features and the distinguishing features. So if I am looking and trying to look and distinguish between these two waterfalls, I'm trying to be able to explain and say why the first one is called Laysan albatross and the second one is called Western Cribbe. I would want to be able to tell that one, despite the fact both have a yellow beak, one has a pointed beak, one has a flat beak or a flat curved beak. One has a red eye, one has a black eye. They both have the same colored wings and body, but the defining and the distinguishing features appear to be in the color of an eye and in the shape of a beak. And that is the challenge, and that is a challenge that explainable AI is trying to solve, to be able to say, to marry the descriptions with the labels. Okay, why is it important? Who should care about it? Why should I care about it? As a data scientist and as all the data scientists in the room, we want our models to not have spurious correlations. In the same example that I had been talking about, I want the model to have been able to identify the object as a bird because of the wings and the beak and the head and the body, and not because of all the blue background or the green background. So now what would happen in most of the bird images would be, they would be taken either in a sky, blue background, in a water, predominant blue background again, or in the trees, green, correct? So the images would have a predominance of this color blue, some spattering of green. Now I don't want those spurious correlations to come in when I'm looking at the images. I want it to be actually, to the recognition of the images, I want specifically these distinctions to be made on the defining features. That's what we want to remove. So unless I know what the model made a decision on, unless I know what we are talking about, as a data scientist, as a modeler, I'm helpless. I can't do a thing about it. The second thing is I want to remove the biases and discriminations. So if you remember, in the morning, somebody talked about the Amazon experience, right? They realized that their models are discriminating against the women applicants. Now, when is the time you would want to find out if you are a developer of that algorithm? Not after it has gone to the production. Not after the world is telling you, why did you do that, right? You want to do it, catch those problems while you are developing the models and be definitely able to fix them. You don't want to discriminate, right? If there's a credit card application that is in, you want to reject it because the income criteria are not met or the credit capability or repayment criteria are not met. Not because of the gender or the race or a zip code. Now in America what happens is zip codes are a very good proxy of your socioeconomic status, also about your race. So you would have the Indian neighborhoods, you would have the Negro neighborhoods, you would have a Caucasian neighborhoods, right? You don't want to use zip codes. Though you are saying it's a zip code, but your zip code is a proxy for so many things. The economic wealth, the race, the gender, the education. Okay? So now you don't want those to come in. So you want to be aware upfront what your model has done. And as in the morning somebody else was talking about, you don't know upfront when you gave the features what did the model learn from this feature or what your feature may have picked up. The way I was talking about the images, upfront I wouldn't know the blue is a color that my image, from an image a model can pick up. Right? And I cannot really remove the blue from my images when I'm talking about it. So the best way for me is if I know after my model has been trained that is it really looking at the blue color in the images while it's doing it. So I want to remove that. I want to be able to debug my models. And obviously I want to be on the right side of the law. So in Europe as well as in US, there are these two laws. In Europe, there is a law called has a law called right to explanation under their GDPR, which makes it mandatory that the models are that impact the general public and the customers and the interfaces be explainable. Similarly, in US, there's a law against discrimination for credit applications. So that's a rather limited law. But I want to be on the right side of the law. Who else cares? The other person who cares is a business user. Now, if a business user does not understand the model, how can I expect him or her to trust the model? And the business user, if they cannot trust the model, they would not want to base their decisions on that model. They would not want to put it in production. They would rather be happy that stays in testing, doesn't go in production, right? So that's where it comes in. Also, a business user would want to know what my model is telling. Is there an additional business insight? Is it something that the model is telling which is going against the accepted domain expertise? If yes, is it just purist correlation or is it worth exploring? Does the model confirm what the domain knowledge is? Same example, does the model confirm a bird has a beak and a wing? Right, so it is where the business user would want it. Obviously, I've already talked about regulatory compliance. One would want to be on the right side of the law. These are the additional sources where you can go and read more about it. DARPA is a defense organization in US which is investing a lot of money in explainable AI. The annual challenge this year is also around the explainable AI. Another FAT-ML is actually another organization which is into fairness and accountability and all. So you can go about, find out what makes models fair and accountable and non-discriminatory. Great resources to go and check out. Okay. Now, if model explanation is so good and since childhood we have been tired of hearing I told you so, why has it not come about? What is it that makes it so difficult to explain the models? See, it was not a challenge for the models to be explainable as long as we were in the world of statistical linear models, linear regressions, logistic regressions. They were all so nicely, neatly explainable. You knew which variables or features are important. You knew how they impacted in general and where your error is, right? It was also easy as long as we were in the world of a rules or a variation of a rules where which says, you know, if this, do that, else do that, or a variation like a decision tree which kind of clearly told you how to split. Where we lost the explainability is when we came into the world of neural networks. Where and why? Because you have all these multiple hidden layers with those interactions and the way it's moving in. By the time you move to a second layer, you have no idea what is going on. We lost it when we moved into words of ensemble learning and ensemble models. Now, what ensemble models did, and if I take an example of random forest, what we are saying is my decision is based on because out of my 10 classifiers, 9 voted in one favor. Now, how do I explain what does these 9 did and why did this 9 did it? Also, once we moved into the kernel functions, right? SVMs, they have those radial kernels. I have no idea what radial kernel means and how do and we moved into the world of hyperparameter tuning. We started saying what my mu should be, what my gammas should be, things like that. And that is where we lost all the explainability. We tried to fit the models which had all these beautiful boundaries, which could dissect the data into very small multiple classes. But in the process, we did not know in high dimensions what is happening and what are the complex interactions that are going on. So, so there are two approaches or two ways of looking at explainable AI. One is to actually look at the models and say and try to figure out in the model itself that what is it doing at each level. And that is what semantic associations do. It actually explains you at this level what is happening. So this is a work which was done by SRI International and by the researchers at SRI International and presented in 2014. What they actually did was they took the neural nets, they labeled each layer, they created a, for each layer they created a label, they labeled it. So each layer they said, if I'm looking at it, what did a model learn? Did it learn a whiskers? Did it learn a fur? Did it learn the claws? They took all these labels, created a sequential, sequence to sequence kind of a model, and then attached it to a cat or a label, so that I know that from a label, I know this is calling something a cat because of the presence of whiskers, fur and claw. So they are using two things. They are using one, a semantic language and a semantic web to understand that whisker, fur, claws, etc. is attached to a cat. Another, they are saying image in the each layer, in the hidden layer, is attached to a whisker, fur or claw. So that is one set of my algorithms which are solving and explaining the models that I have had in its layer. So this is actually trying to make my neural nets kind of models more explainable. Okay, this is another example. They took it, the same researchers took it to the videos. They actually sat down and labeled the frames within the videos and said, okay, if I look at each frame and if I'm looking at a person attempting to do a skateboard trick, what all would happen? So another example they had is about the wedding. And they said in a wedding you would have exchange of rings, you would have exchange of vows, you would have a celebratory drink. It's a US setting. So they're looking at all these videos, they're looking at those sequence. Again, they're fitting in the sequence to sequence model for the sequences and a semantic web, and then coming out with the labels. So it is very inherent to the way the model is working. The other one is what is called Lime. Highly popular these days, has libraries available in Python, R, everything. Most of the open source libraries are available for this. And there are variations to it called Anchor Lime, etc. Essentially what Lime is doing is, Lime is making a complementary model. It is not touching your black box model. It is not telling you what your model did and why did your random forest come out with the explanation, come out with a prediction or a value that it came out with. It is not doing any of that. What it does is, it takes a simple linear model, which could be a decision tree or a linear regression, fits it on a model output and says how well can I explain it. And if that explanation fits well, then it gives that as an explanation. Basically what it's saying is that all my models at each level are linear in space. So my entire boundary condition could be curved, but wherever I'm making a decision, that space is flat and that space is linear, and that's how it's explaining that linearity. So in this image, they would be classifying the image, original image, and say, this region tells me it's an electric guitar, this region tells me it's a Labrador, this region tells me it's an acoustic guitar, etc. Put it together and give you a description. If I look at it and, okay, I'm running out of time, but you know, this is an example I would have loved to spend a little more time on. So this is basically my tabular data, simple data which is trying to predict what a person's income would be based on their demographics, education, etc. Now if you look at it, the example on the left is basically what the descriptions and what the values are for each of the feature. The AI model, which was a random forest here, predicted that the income is going to be greater than 50,000. And then a linear model, a decision tree came out and said it would be greater because I found these values, everything that you see in blue, I found these values to exist in this example and therefore it is true. Now I may give the same explanation. I would be 96% of the time correct and consistent with my AI prediction, 4% of the time I'm wrong. These are the two examples. The one on the left is the one on the left, correct. The one on the left is the one which is correct example, where the AI and the explanation are both consistent. The one on the right, the explanation is the same, but the model, AI model actually predicted income to be less than 50,000. If you look at all the values, where they actually differ is on the work class. The example on the left, work class, the second element from the top is private sector. The one on the right, it is a state government. So AI model made a difference, your prediction or the explanation couldn't, and that's that 4% where the errors would be. Similarly, same example, this is a case where it is 100% consistent. Another example from the same data set, the explanation is different. So explanation that is coming out is very specific to the use case or the row element that you're looking at. It is not a generic explanation. It's not like just telling you your global features and the importance of global features. And how you decide, so you be looked at 96% and 100%. In a code somewhere you give a threshold value. So when I ran the code, I gave a threshold value saying that the models would have to be 95% of the time consistent. Otherwise, don't accept the explanation. Okay, that's all I have for. That's all I have for my presentation. I will be happy to connect with you either offline or right now, if you have any questions. I would urge all of you to actually go and check out Lime. Actually the researchers have made their entire GitHub library online and available for free to use. They've come out with a further variations called Anchor Lime and etc. H2O and most of the packages and most of the open source libraries have picked it up, and it's fairly easy to use. Please go ahead, experiment, explore. It's a very cool thing to do. It doesn't explain your models the way they were created, but it still gives you an explanation and tells you where are your blind spots, where your correlations exist, spurious correlations and biases and discriminations, which as a researcher and as a business user I need to worry about. So that's it, that's from me. Yeah.
Is this an alternative for black box?
It is. Explainable AI means I want my black box models explainable. It is.
So it's scalable as well?
Yes, it is. I have experimented a lot with Lime. I have not faced an issue with either scaling it up or having a problem with the explanations. The only challenge that I do face is that, I cannot, so every time I run it and it gives me a explanation, it tells me it applies to about 2% coverage. Now for me to sit down and figure out what are the various 50 explanations and where could the biases coming in, that becomes a tedious task. But so that's probably the only challenge that I see per se. And their next version, Anchor Lime, has is more sturdier. So I haven't faced any challenge with this. Yeah.
Does the training data require more complex labels?
No, nothing. Because see, the beauty with Lime and Anchor Lime is that they're independent. So you can have your black box model, your random forest, your ensemble learning, anything, it doesn't matter, XGBoost, whatever, neural nets. You have your independent model, you have your black box model independently working, you have your explanation working independently. Your explanations are linear regression and decision tree models most of the time, which are not very heavy on any of the requirements, whether it's a feature set or it's a data set requirements. So one doesn't face much of a challenge there.
If you see the example, the different types of birds.
Correct.
So if you are just classifying that, you just have to label the types.
Yeah, please go ahead.
But if you want to add the explanations, you also have to label it with the different types.
Correct. You have absolutely hit it on the head. See, if I am looking and trying to explain my model from the beginning, the way my semantic associations does, it becomes really heavy on the manual labeling front. To be able to sit down and label each my hidden layer, to be able to create the sequence to sequence model, and I say, which says fur and whiskers and claw together add up to a cat, it does become a time consuming job. But it's much better in the sense because it's coming from your original models. Your shortcuts are your Lime and Anchor Limes. Really the way the world should work is more like your semantic associations. Any other question? Yeah.
So for deep networks, you said that Lime can be used to understand the deep networks working and all. So generally the explanation is in terms of the linear models, right?
Correct.
And deep networks are non-linear functions.
Correct.
So how can you explain the non-linear decision using linear functions?
Okay, do you remember tangency that you would have heard in school? You have a curve, but at a point it's linear. And that's the basic crux of line models. So your models could be shaped anywhere. When I'm trying to define, I'm defining a model at a point. And at a point it's linear. It is assumed to be linear and therefore my linear model can explain it.
Okay, so you are explaining the output of the entire model?
You are explaining the output of that particular element, and that's why I showed you two different examples. In this example, where my line model explanation is consistent with my black box model, it is consistent 100% of the time and the explanation is pertaining to only 3 features. For the other example, it is consistent only 96% of the time and the explanation spans about 7-8 features. So the explanation is very specific to the point or the element we are talking about.
Okay.
Okay, we'll have